Timescale content caching and user association with 5G heterogeneous network. Abstract. In this paper, we develop a content caching and flow level BS user allocation framework in a network environment with a special variant of content popularity. Because the studied content caching and BS user association function are tightly intertwined with each other, and their decision time scales can be very different in practice. Our design considers the time scale separation of these network functions to tackle and then develop the BS user association and content caching policies. Specifically, we propose an optimal BS user association algorithm, namely OptUA, operating in the short time scale for a given content caching solution, and greedy content caching algorithm, namely GCC, operating in the long time scale. The GCC algorithm exploits the submodularity characteristics of the objective function, which ensures that the GCC algorithm achieves a constant fraction of the optimal performance for most feasible caching sets. Via extensive numeric studies in heterogeneous cellular networks, we demonstrate the proposed OptUA and GCC algorithm outperforms other algorithms which do not consider special variations of content popularity in terms of average end-to-end delay per content request and average system load per content at each BS. Introduction. As the demand for mobile video data increased exponentially in recent years, efficient content caching plays a vital role in future 5G wireless networks. Many content caching algorithms 2 to 5, which cache popular content and network edges closer to the users, have been proposed to significantly elevate the traffic load in the core network and improve the end-to-end service latency. However, most previous works have not captured the spatial temporal dynamics of content request. In fact, content popularity patterns can vary over the time and space in practice. For example, Yankees baseball game is likely to be more popular in Manhattan area at a specific time zone than in other areas or different time zones. These spatial temporal dynamics of content popularity patterns are very similar to variation of spatial traffic patterns over time. 6. Except that the content popularity patterns can have much finer granularity than the traffic patterns due to the heterogeneity of content types. In addition, any user requesting specific content typically wants to be associated with a BS which provides a high end-to-end service rate to the users. This association decision also depends on if the BS caches to corresponding content. Therefore, content caching decisions must be made jointly with BS user association decisions. In this paper, we formulate the joint content caching and BS user association problem to optimize the flow level network performance. For example, load balancing and end-to-end delay, considering the spatial temporal dynamics characteristic of content popularity patterns. Even though there have been some recent works dealing with joint content caching and BS user association problems, C223, they assumed fixed or general content popularity and did not capture different time scales of these network functions. To that end, we addressed our flow level BS user association optimization problem in our design similarity to the previous works, 6 to 7, which aimed to achieve both efficient load balancing and delay optimization for all networks flow without considerations of content caching in BS. However, we would like to emphasize that our problem is more difficult to solve than those in the previous works. This is because the spatial heterogeneity of content popularity is incorporated in our optimization framework, and number of possible solutions of content caching at all BS is much higher for our considered problem than those of BS on-off activation solutions in previous works 6. Because finding an optimal solution directly for the considered joint content caching and BS user association problems is challenging, and 2. The time scales of flow level BS users association and dynamics of content popularity patterns are very different. We take the time-scale separation design approach to develop the BS user association and the content caching control algorithms in our design framework. Specifically, we propose a short timescale optimal BS user association algorithm for a given content caching solution, which can be implemented in a distributed manner, and a long timescale greedy content caching algorithm which guarantees to achieve 1 minus e/1 of optimal objective value for most possible content caching set. The contribution of this paper can be summarized as follows. First, we formulate the joint content caching and the BS user associated problems, which aim to optimize flow level network's performance. For example, load balancing and end-to-end delay, considering the spatio-temporal dynamics of content popularity. Second, we propose an optimal BS user association algorithm, namely OptUA, for a given content caching solution. Moreover, we propose a low complex greedy content caching algorithms, namely GCC, which operate on the long time scale with the OptUA algorithm is running on the short time scale. We show that the GCC algorithm guarantees to achieve a constant fraction of an optimal objective value for the most practical cases by exploiting submodular property of the objective function. Via extensive simulation studies in heterogeneous cellular networks, we show that the proposed OptUA algorithm enables mobile users to be associated with BSS that cache the corresponding content to optimize flow level network's performance. In addition, the proposed GCC algorithm, considering the outcome of the OptUA algorithm, outperformed the other general popularity based caching and random caching algorithm thanks to the explanation of spatial heterogeneously of content popularity. In this rest of the paper, we begin with the description of the system model in section 2. We present the joint content caching and BS user allocation problems in section 3. In section 4, we propose OptUA algorithm and the GCC algorithms. We evaluate the performance of the proposed algorithms via extensive simulation in section 5, followed by the conclusion in section 6. System model. Second, we consider a cellular network which consists of multiple BSS with finite caching capacity. Let us denote the content set of F, where the file size each content is denoted by U in bits. In addition, we assume that all contents are stored in their own servers distributed throughout the internet. We consider particular geographical region R-square served by the set of BSB. Let XL denoted some specific location of interest and B denoted with the BS index. We assume that content requests for content F arriving at the location X according to an inhomogeneous Poisson point process with average rate per unit area equal to lambda F. Then the corresponding traffic load can be expressed as lambda F x U. It can be observed that this traffic model enables us to capture spatial heterogeneity in dynamic content request. Let us denote the caching decision variables I equal where I f n. If content f is cached in BSN, otherwise I f n equal 0. Equivalently, we also introduce a vector S whose set element represent the set of cached contents in different BSS, where is Sn denotes the set of cached contents BS and foursquare. Because the time scale for updating contents caching decisions must correspond to the time scale over which the content popularity variables varies. For example, few hours, we assume that you assume the time scale for updating content caching decision is much longer than that for making BS users association decisions. With these defined caching decision variables, finite caching capacity constraint and individual BSS can be expressed as follows, where Tn denoted the caching capacity of BSN. For a given caching solution, S is or BSS. The average end-to-end data rate from BS the average end-to-end data rate from BS and B, the original content server, of each content location X for content F can be calculated as where C, F, B, and X denoted the average wireless data rate for content F between BSN and a user at the location X if the content is cached by the BSN, and the C denoted average end-to-end data rate from the closest content server which stores content F to users at location X via BS, and where C, F, E, and X mean C, F, A, and where CFSN expresses the backward data rate to support data delivery from the content server of content F to BSN. Note that CFB, BNX, and CFA and denoted the average rate where the effects of wireless fading or dynamic intercell interference are averaged out. This can be justified by the fact that the time intervals over which caching and BS users association control decisions are made are large, for example, a few minutes to hours. These assumptions have also been adopted in previous load balancing works. Using these definitions, the load density sigma Fn can be defined as like this, which represent the fraction of time required to deliver content, load content BS location X. In addition, we introduced the routing function PPF XN probability that user flow content associated with BS, and intuitively PFNX can be interpreted as a time fraction that a flow of the content F arriving at location X is routed to BSN. It turns out that the optimal PFNX will be either 1 or 0. For example, deterministic routing or BS user association is the solution of our optimization problem defined later in P. We now provide the definition of content load feasibility for each BS in the following. Definition 1. Feasibility. The set H is feasible content load BS. For a given content caching solution, BS is defined as where is arbitrarily small positive constant. Note that any feasible BS in the content load row has corresponding routing probability vector Px, P1 to 1, or XL. Proof. It can be easily proved using typical definition of convex function and the consideration of heterogeneity of content probability. The detailed proof is presented in our technical report, problem statement, and then two-time scaling design approach. Problem formulation. Our design problem P aims to find an optimal set of joint cache contents in each BS and BS users association solution, for example BS load row, which minimize the flow level cost function as follows. Mean A constraint 1. The flow level cost function A lambda is designed based on alpha delay performance function in 6. However, we additionally take into account content diversity and backward data rate in the original alpha delay performance function as follows. where alpha denoted a trade-off parameter between load balancing and minimalized to total BS and content load. When alpha equals 0, rate optimal A0 becomes alpha n sigma f rho f n. When alpha equals 2, end-to-end delay optimal A2 becomes, which is equal to the total average number of serviced contents in the system if we consider the system as an MGI multiclass processor sharing system 11 from the little row minimizing A2 equivalent to minimizing the average end-to-end delay 5. For each content request, other cases and details are presented in the technical report 10. Timescale separation approach. It is very difficult to solve the general problem P because the BS user association problem and content caching problem are tightly intertwined with each other. To facilitate the algorithm design, we assume a timescale separation design rationale exploiting the fact that content request arrival and departure and the corresponding BS users association decision occur on a much faster time scale compared to the time scale over which content caching decisions are updated. Since the time scale for BS content caching controls is similar to that of the content request pattern variations, this time scale is apparently much longer than that for flow level BS user association. That is, the time scale can be separated between the BS user association and the content caching decisions. Leveraging this time scale separation, the problem BS user association problem for given caching solution, for example, the content caching vector I, problem P, becomes the following short time scale problem, BS user association problem. Solving this problem is equivalent to find the BS user association set P. Content caching problem. The longer timescale problem aims to find a set of contents to be cached in each BS as follows. Content caching problem PCC, where the objective function GI corresponds to objective function PUA with the optimal BS user association solutions. Number 4. BS user association and content caching algorithms. Short time scaling BS user association algorithm. The short time scaling BS user association algorithm can be similarly delivered as a 6 except that content diversity is considered in our design. Optimal BS user association policy. We denoted the optimal BS load vector as rho, which is solution of the problem PUA, and denoted the optimal BS user association solution for content F at location X as NFX. We describe the optimality condition of the problem, which is used to develop an optimal BS user association policy in the following theorem. Theorem 1. If the problem P minus UA is feasible, then the optimal BS with which a user location X requesting content F is associated is given by proof. This theorem can be proved using the standard optimization theory. The proofs presented in our technical report. Long time scale content caching algorithm. Rationale of the content caching algorithm. The object function GI is the non-convex and discontinuous function because of discrete decision variables I. Hence, the content caching problem is combinational problem with order 2 possible solutions, which is difficult to solve when the numbers of contents and BS are large. Fortunately, the objective function G rho I is convex in rho, and its optimal solution can be determined for a given I or S. Note that the function GI equals GS when A rho I. Rho HI is obtained by applying opt UA policy given in section A. Moreover, the function GS is surjective verification for the submodular set function with alpha equal 2, where S1, S2. function. For example, the exact optimal value of GS exists for all possible caching sets Sn for all and B. Then we can consider an equivalent objective with a P in the following: IP max HSST constraint, where H is G pi minus GS, where rho means empty set. If the objective function HS in IP is a non-decreasing submodular set function, 12 show that the non-modified greedy algorithm caches achieves 1-1 per E performance of the optimal objective function values. To exploit this result, we verify whether the function HS is non-decreasing submodular and submodular set function or not. The definition of the submodular set function is given as follows. Definition to a real valued set function G defined on subset of finite sets F for or BS is named submodular set function if it is satisfied the following condition for or SS prime and or Fn F per Sn prime B. It can be verified that the objective function HS is a submodular set function for most feasible caching set for other values of alpha. For example, 2, 3, 4 via numerical test. The cases with alpha equal to illustrate the figure 1 is summary a known greedy algorithm 12, which is slightly different from our proposed algorithm described in the following guarantees to achieve 1-1 e per 1 of the optimal objective function value HS for most feasible caching sets. Inspired by these facts, we propose a greedy content caching algorithm is following. Greedy content caching algorithm. We first describe a greedy content caching algorithm called GCC that iteratively caching contents so that it can achieve the most reduction in the objective value. The main idea of the GCC algorithm is to iteratively cache contents in BS one by one, considering the global object reduction for all contents in all BS until caching capacities in all BS are completely filled up. As discussed before, contents caching are corresponding BS user association decisions are coupled over all BSs. Hence, we need to carefully cache contents considering the current content caching and BS user association status in our BS. Greedy content caching algorithm. In steps 3, 4, and 5 of the GCC algorithm, we verify whether the caching capacity of the BS is completely filled up or not to reduce the searching space and the calculation effort of the greedy caching matrix. In step 6, we calculate the caching matrix MGFM for all uncached contents in our BS except for BS whose caching capacities have been filled up. In steps 7 and 8, we find contents F in BSM, which minimize the greedy matrix MGM, FM, and cache this is best contents F in BSM. Note that in each iteration, the GCC algorithm only caches one content in one BS, which minimizes the caching matrix. Therefore, if maximum number of contents which can be cached in each BS is 10 and the number of BS is 10, then the maximum number of iterations performed by the GCC algorithm is 10 times 10 equal 100. We believe that the proposed GCC algorithm brings a significant performance enhancement because it attempts to cache the best content in each step using the metric, which is the value of the G obtained after optimizing the BS user association decision variables. This algorithm also exploits the structure of the objective function and caching constraint in P, which account for the heterogeneity of content popularity and current caching and the BS user association status in all BS to make content caching decisions. 5. Performance evaluation. Simulation setup. We evaluate the performance of the proposed joint content caching and BS user association algorithm via extensive simulation under various configurations. The consideration network topology consists of 5 macro BS and 5 micro BS in 2 times 2 kilometer scale, as shown in figure 2. We use mean transmission powers BS given in 13, which are 20 watt and 1 watt macro and micro BS respectively. We consider 100 different contents with the same size of 10 megabytes. Moreover, we assume that the BS can cache up to 10 contents. Other parameters for the simulations set according to the IEEE. Figure 2. Snapshots of cell coverage for contents 11 by different user associating algorithm with the random caching policy alpha equal to 802-60 evaluation methodology document 14. In addition, we assume contents in each BS receive the same fraction of scheduling time. Hence, is same for all contents. The data rate from original content servers to each BS is set to be 100 kbps, 1 megabps, which are the average values drawn from a real YouTube dataset. We consider 2 objective functions corresponding to different values of alpha in the simulation study. The average system load per each content in the BS alpha equal 0 and 2. The average content services delay alpha equal 2. In addition, we compare the performance of the proposed caching and then BS user association algorithm with that of the following algorithms: flow level BS user association FLA in 6 and 2, nearest BS user association MBA under 2 baseline caching policies, random caching, and the general popularity GP based caching. The random caching policy caches the contents in each BS in the random manner until the caching capacity is filled up, while the GP-based caching policy uses the general popularity. For example, all BS assume the same popularity profile for all contents. The FLA algorithm does not consider the heterogeneity of content popularity over different contents, but take into account only the total urban rate. For example, lambda fx for each location x. Moreover, each user is associated with the nearest BS under the MBA algorithm. Simulation result. We carry out the simulation under 2 different content request scenarios. First, homogeneous content request distribution. For example, lambda f x lambda f for all f and then for xl, where lambda f follows the zip distribution 16 for all contents, and heterogeneous content request distribution. For example, lambda fx varies from content, location to location, and then content to content. We assume the Gaussian distribution with mean lambda f and variance lambda scale. We discussed the simulation result and the key observations in the following. Impact of caching aware BS user association with the cell coverage. First, figure 2 depicts the snapshot of cell coverage for one specific content by different BS user association algorithm with the random caching policy when alpha equal 2 in the FLA algorithms. Many users prefer to associate with the macro BSs to attain higher data rate, whereas all users are associated with their closest BS in the MBA algorithms. Moreover, in the opt-UA algorithm, the cell coverages of BS which have the corresponding content 11, are larger than that due to other BS users association algorithms, since the opt-UA efficiently exploit caching status information in all BS to achieve the best objective value. We now evaluate the performance of the proposed GCC algorithm in conjunction with different BS user association algorithms and other content caching algorithms in conjunction with the proposed opt-UA algorithms. Impact of the backhaul data rate. Figure 3a-b depicts the average system load per content in each BS and the average service delay per content request versus the backward data rate. As the backward data rate decreases, the GCC algorithm attains higher performance compared to the other caching policies in both performance metrics. In particular, the opt-UA GCC attains 25 lower average delay than the opt-UA plus GP and 60 lower average delay than the opt-RAND, where the backward data rate is 0.1 Mbps. This is because GCC algorithm takes into account the spatial heterogeneity of content popularity in making cache decisions. Hence, more content requests are served from BS as the cache corresponding content under the GSS algorithm. Whereas other caching algorithms tend to retrieve the request contents from their original content servers more frequent and use backward links. Impact BS user association algorithm. As shown in figure 3a-b, the proposed GCC algorithm attained the best performance when it is jointly used with the opt-UA algorithm compared to scenarios where other BS user association algorithms are employed. This is because GCC algorithm can take into account the objective function value G, which is a function of the optimal BS users association seeks to make content caching decisions. Moreover, FLA algorithms, which with GCC algorithms outperforms the MB algorithm with the GCC algorithm is inhomogeneous content request distribution scenarios because under the FLA algorithms, BS user association decisions account for the spatial variability of traffic distribution. Impact of a spatial heterogeneity of content popularity. Figure 3 depicts the delay performance of the opt-UA plus GCC algorithms compared to the opt-UA GCC algorithm as a function of the average system load per content of BS, average delay per content request. Impact of spatial heterogeneity popularity. Figure 3. Performance of proposed BS user association and content caching algorithms in heterogeneous content request. Scaling factor, which captures the degree of spatial heterogeneity of content popularity. As the scaling factor increases, for example, it increases spatial heterogeneity of the content popularity, the performance gap between opt-UA GCC and the opt-UA GP becomes larger. We can see the average service delay per content request due to the opt-UA plus GP is almost twice of that when the scaling factor is equal to 0.9. Concluding remarks. In this paper, we have studied the dynamic content caching and BS user associating problems considering the spatial variation of content popularity. To tackle this challenging joint problem, we have proposed the online optimal BS user association algorithm operating on short time scale for a given content caching solutions, and the greedy content caching algorithm operating on the long time scale. Through the extensive simulation in the heterogeneous cellular networks, we have showed the performance gains of the proposed algorithms against other existing algorithms into performance metrics, namely the average service delay and the average system load per content in each BS.